Hey there, guys. So, a couple of weeks ago, we were discussing why the special theory of relativity was introduced by Einstein. We looked at a bunch of basic concepts and we took a dive into the context in which the theory was developed. So, back when Albert Einstein was in his 20s, in 1890s and 1900s, there were these two principles in physics: the principle of relativity, which the requirement that the laws of physics must be obeyed in all inertial reference frames. And then there was the principle of light constancy, the requirement that light should have a constant speed independent of the frame of reference. And these two principles were in contradiction with each other as long as Galilean transformations were used. And this contradiction had to be overcome. Something had to be done to solve the contradiction and make these two principles be consistent with each other. Different people were trying to find different solutions, and Albert Einstein was the one who solved it ultimately. Last time we looked into these principles and the basic concepts that lead to them in detail. So, if you have forgotten or if you hadn't watched the video, I recommend you that you go back and brush it up once. So, now we'll be moving forward and see what Albert Einstein actually did. So, we saw that Albert Einstein believed that Maxwell's theory was right, Maxwell's electrodynamics theory, which gave rise to the principle of light constancy. He believed in it. So he thought that it's the Galilean laws of transformation that need to be changed so that the principle of light constancy and principle of relativity be made consistent with each other. So he looked into the Galilean transformation laws and he found this, that we were assuming, we were taking for granted that two different observers in different states of motion would measure time intervals do the same thing. Einstein thought that was a given. That might not be so. So he devised a thought experiment to test if that was true. And we will look into exactly that now. So move forward. So for this part of the video, I'd like to use the blackboard, not the blackboard, the whiteboard. So we saw that Albert Einstein thought that the problem was to do with a particular equation in the Galilean transformation equations, which was this: that if there was an event happening and two people were observing that event, and if they make a time measurement, suppose there are two people A and B, the first person A measures the time taken for the event to happen as T sub A, and the second person measures that to be the time taken for the same event to be T sub B. Laws of Galilean transformation assumed that these measurements would be equal. All observers, irrespective of their state of motion, would say that the same event takes the same time to happen. Alright, T sub A equals to T sub B. And this was the line that Einstein thought was fishy. Right? Uh, this assumption led to the violation of principle of light constancy. Different observers would observe the measure the speed of light to be different, which was not supposed to be so if we assume that Maxwell's theory was right. So Einstein wanted to test if we assumed that all observers in all sorts of reference frames, all sorts of states of motion, uh, perceive the speed of light to be the same number, what happens to this equation? Will it stay the same, or will we need to change something about it? Right? And he even devised a thought experiment with which he could test it. And we will look into that. Okay, so let us suppose that there was an observer, somebody here, and let us label this observer as A. This observer has a setup with themselves. They have two mirrors, a mirror here and another mirror right below. They have two mirrors. What they're going to do with these two mirrors is they have lasers, say, and they send a pulse of light upwards. This pulse of light goes upwards, it hits this mirror. Let's label the mirrors P and Q. It hits the mirror Q, it hits the mirror P, it is reflected from mirror P, travels downwards. Travels downwards, it reaches mirror Q, it's reflected again, it goes upwards. Reaches mirror P, reflected from mirror P, travels downwards to mirror Q, reflected from mirror Q, up to P again, P, Q, P, Q. So light is doing this round trip, right? And we know that
Light does this round trip with a velocity c, which is a constant. And we know c to be c, which is a constant. Happens to be 3 times 28 meters per second. Right? Um, we also know that the velocity is distance traveled divided by time. So what we can do is we can give a stop clock to this observer here, right? They have a clock with themselves. And what they're going to do with this clock is they'll start their stop clock as the pulse of light leaves the mirror tube. They'll wait, the pulse of light goes upwards, it is reflected from mirror B, it comes back to Q. And right when the pulse of light reaches Q again, they stop their clock. So they measure a time interval. They are essentially measuring the time taken for this pulse of light to go upward and come back. Time taken for this light beam, light pulse, to undergo one round trip from Q back to Q. Okay. So let's call this measurement, let's call the time interval, whatever this observer measures on this clock, it's delta T T. Okay. Delta T meaning time interval sub A as measured by this observer A. Okay. And we know that this C here is distance traveled by time taken. So let's label this distance, the separation between the two mirrors, as small letter m. Okay. So what is the distance traveled by the light beam, light pulse? It goes a distance, it goes up a distance L, it comes back a distance L. So it is traveling a distance 2L. And the time taken for it to do so is measured by our observer here using their stop clock to be delta T sub A. So the velocity of light by the definition of velocity. This number here, 2L, twice the separation between the two mirrors, divided by whatever number the observer measures using their stop clock. All good. What we want to do now, we'll take this whole thing, the observer A and their mirror set up their stop clock. We'll put the whole thing inside a rocket. Okay? We'll put the whole thing inside a rocket. And the rocket is now moving. With respect to another observer who is standing outside the rocket. There will be another observer. Right? This another observer is now labeled as B. They have a clock with themselves. And the relative velocity between this rocket and observer A and their setup and this observer B, let's call it U. Okay? So write it more clearly. So here is this rocket moving with the velocity u with respect to the observer t. Okay? So this mirror setup in which light is going up and down is moving with respect to observer b with the velocity u. But with respect to observer a, these two mirrors and the whole system is at rest. Okay? Now this guy also has a stop clock. Okay? They are also going to make a measurement. Observer B also makes a measurement. He measures the time taken again for a round trip from Q back to Q as delta T sub B. Delta T sub B. What I'm asking now is, are these two quantities equal, delta T A and delta T B? We have to assume that the velocity of light is measured to be the same thing by both the observers. That's what the principle of light constancy demands. So let's take a look at what happens in the frame of reference in this time. I'm going to erase my diagrams now. Okay, so this is what was happening in the frame of reference of observer A. The standard names used are Alice and Bob for A and B, so let's stick to that. So in Alice's frame of reference, there were two mirrors and light was so there were two mirrors and light was just going up and down because the whole setup was at rest with respect to Alice. But when we go to the second observer, observer B, whom we can call as Bob, they see something different happening. Right? Light is going up and down. As that happens, this whole setup is moving with respect to them inside the rocket. So as light is going up, but as it goes up, this mirror, the whole thing is moved. So they see that light traverses a diagonal path. Similarly, as light comes down, they see that the mirror setup is moved because it is inside an object that is moving with respect to them. So Bob will see that light again traverses a diagonal path. So effectively, while Alice sees this thing happening, light just going up and down and up and down and up and down, Bob sees something different, light traveling in diagonal paths, zigzag paths, right? He sees this instead of that. So what is seen between both the observations is that the velocity of light is measured to be the same number, c, because that's what the principle of light constants demands, right? So, so here also light is traveling speed c, same here. Here light travels a distance 2l, as we have seen. Here the distance traveled is definitely different. Okay? L is this separation over here. This is L. But the distance light is traveling in Bob's frame of reference is not L. L is the vertical separation. There is also a horizontal component of the separation. The path is diagonal. So let's figure out what this distance here is. So the rocket was moving with velocity u, and it covered this much distance while light traveled up and came back down again. The time taken for light to do so was measured by Bob using his stop clock v delta t sub v. Okay, so this was the time taken. By definition of velocity, the velocity of the rocket u is the distance traveled by the rocket. It's called v. The distance traveled by the rocket divided by the time taken, which is delta t sub v. Okay? So what is this distance? It is exactly this separation here. So this separation E is nothing but U delta T sub P. So this separation here is U delta T sub P. Okay. So now we know the separation. We know what this diagonal distance is. Let's call it capital L. So using Pythagoras theorem, which we all learned in high school, I can say the square of this capital L, the square of the hypotenuse L square is equal to square of the horizontal distance, which is our small l, which we are all familiar with, plus the square of this guy, actually the half the square of this guy. So this distance here is half u delta dv. I'm only interested in the distance traveled from one mirror to the other. Okay, so this distance here is uh, u square delta dv square divided by 2 square, which is 4. Okay, let's keep this in mind. Right? Okay, so we have this equation here, which tells us what the speed of light should be in terms of the distance and time measurements made by the first observer, Alice. Okay. Let's try to write a similar equation in terms of the measurements made by observer B or Bob. So the speed of light has to be the same in both frames of reference. Okay. But the distance is going to be different. The distance traveled by light for Alice was just twice small l. Small l is just the vertical separation. Okay. Distance L up, the distance L down. But Bob sees something more complicated. Capital L and capital L. So he's going to see twice the distance capital L divided by the time that he measures on his stop clock. This is delta dB, delta T sub B. Right? But we know what capital L is in terms of small l. I have a square here, I can remove that by taking the square root. So I put a square root around here. Okay? So I can put that. So now I can say C is twice small l square plus u square delta dv square divided by 4 whole divided by delta dv. So the whole thing divided by delta dv. Okay. So let me make some room to write down both things. Alright, so I've just made some room for myself and written the equation up here. So what I can do now is I need an expression for small l. So I can use this equation, rearrange the terms in this equation to find an expression for small l. I simply transpose a couple of terms. Small l turns out to be c delta t sub here divided by 2. That's what small l turns out to be. Now I can square this and plug it into this equation. So c will be 2 times root of, I mean l square. I can just square this c square delta t a square, and 2 square would be a 4 in the denominator, but I also have another 4 over here. So I'm going to write a common denominator now inside the root plus u square delta t p square whole divided by delta t p. Now there are a lot of simplifications that I can make. First of all, I have a 4 inside the root. If I take this outside the root, it will become a 2. Right? 4 is nothing but 2 square. If I pull it out of the root, it becomes just 2. And I can cancel the 2's. Right? So I get rid of the numbers. Okay? Now I have a square root here. I don't like the square root. It complicates things. I want the square root to be gone. So I can square both sides of the equation to get rid of the square root. So I square the left hand side. C squared is now equal to delta t squared in the denominator, and the square root will be simply 1. What else can I do? I can transpose this delta t squared to the other side to make it more neater. Right? So c squared delta t squared be equal to c squared delta t a squared plus u squared delta t b squared. What I'm going to do now is I want to group the terms that have a delta t square in them. Right? I have one here, I have another one here. I want to group them together. So I send this term to the left hand side. It will obtain negative sign. So I have delta t square times, I had a c square already here. Okay, I had a c square. I also get a minus u square as I'm sending this term to the left hand side. Square is equal to c square delta t square. Okay. I can make further simplifications. I can take this c square and send it to the denominator on the left hand side and write delta t square times c square minus u square divided by c square is equal to delta ta square. So now I have a neat equation which gives me a relation between delta ta square and delta tb square, delta tb square and delta ta square. We can slightly simplify the c square minus u square by c square. Let's try to do that. We can further simplify this c square minus u square by c square. So if I divide c square, I can distribute the c square over both the terms. C square by c square is just 1. So I'll get 1 minus u square by c square times delta tb square is equal to delta ta square, right? Or I can send this term to the denominator on the other hand. Delta tb square time interval as measured by Bob is related to the time interval, square of the time interval as measured by Bob is related to the square of the time interval as measured by Alice. This is the guy outside the rocket, this is the person inside the rocket, divided by this term that I have over here. 1 by u squared, 1 minus u squared by c squared. Right? I have squares of time intervals here. I don't want that. I want a relation between the time intervals themselves, not squares, but delta TP and delta TA themselves. So I can take the square root on both sides of the equation and I will obtain something that looks like this. Delta TB is equal to delta TA divided by the root of whatever I had here, whatever I had. Let me write the same thing above it. Right. So this is the equation we'll obtain in the end. And it's a very famous equation. It's known as the time dilation equation. And it gives us a relation between the time interval taken for the same event by Bob outside the rocket, moving with respect to my mirror apparatus, and the time interval for the same event as measured by Alice, who was at rest with respect to the mirror apparatus. Now we can ask ourselves, will they measure the same time? Or will they measure it differently? What condition is required for the time intervals delta t sub b and delta t sub a to be same? For that to be the same, I want this term here to be 1, right? I want the denominator to be 1. When will that happen? When u is 0, you can read it from the equation. If u is 0, 1 minus 0 is just 1, square root of 1 is 1, delta Ta divided by 1 is also just delta Ta again. So delta Tb and delta Ta will be the same. So what this equation tells us is that suppose there is an event happening and suppose there are two observers such that there is no relative velocity between the two observers. Right? U must be 0. The two observers should not be moving with respect to each other or with respect to the system. Then both of them will measure the same number if they are asked how much time did it take for the event to happen. What if it's different? What if one of the observers is moving relative to another observer? Then things will look slightly different than what one might expect in classical mechanics. So, see, we have a square here, u square, which means regardless of what u is, what direction the motion is happening, direction the relative motion is happening in, u square is always going to be a positive quantity. So, I have 1 minus some positive quantity. So, this quantity here is going to be less than 1, right? So, if it is less than 1, the square root of that is also going to be less than. If my denominator is less than 1, then the whole thing will turn out to be greater than 1, which means delta TB will turn out to be greater than delta TA. Okay?
Right, let me switch back to the slides now. As we just saw, the time taken for the same event to happen was different for two different observers, all right? Here is the time measured by Bob, and here is the time measured by Alice for the same event, light going up and down. But if there is a relative motion between Alice and Bob, if u is greater than 0, if u is different from 0, delta TB is going to be greater than delta TA, which means suppose Alice inside the rocket says it took 2 seconds for the light pulse to go up and down, Bob outside would say, no, it took 3 seconds or 4 seconds or something like that. This is very counterintuitive, but that's what you'll obtain if you assume that the principle of relativity and the principle of light constancy are both true, which is what Einstein did. And he achieved this equation. This phenomenon in which two different observers measure the time taken for the same event to be different is called time dilation. Okay? And the time measured by an observer who is in motion with respect to the system is called as dilated time. So this delta TB is called as dilated time, whereas delta TA is called proper time or eigen time, right? So this time measurement was made by Alice, who was at rest with respect to the mirror apparatus. Therefore, this time measurement is called proper time. Every time an observer makes a time measurement while being at rest with respect to the system that they are making the measurement of, the measurement is called proper time or eigen time. Whereas the time measurement made by an observer who is in motion with respect to the system in which the event is happening, of which they are measuring the time of, their measurement is called the dilated time. And dilated time is always greater than proper time. We just saw that. If I plug any non-zero value for u here, since it is squared, ultimately you'll obtain delta TB greater than delta T, which means dilated time is going to be greater than the proper time. If both the observers happen to be at rest with respect to the system, or both the observers happen to be at rest with respect to each other, you will see that they will agree with each other about the time measurement. In that case, proper time and dilated time are going to be one and the same thing. So people will agree that time is same for everybody when they are at rest with each other. If people are moving with respect to each other, their time measurements for the same event will be different, which means time is different for different people. It's not an absolute quantity. Such a shocking result that Einstein reached, assuming that these two principles, the principle of relativity and the principle of light constancy, uh, have both to be true. But if time is different, if the time taken for the same thing is different for different people in different states of motion, why don't we see it in our everyday lives? Okay. And the answer to that is because c is such a large number. This thing here, 1 divided by root of 1 minus u squared by c squared, it has a name. It's called Lorentz factor. Okay. And it is denoted as gamma, right? 1 by root 1 minus v squared by c squared. I have B here I had during my previous slide. I hope you can adjust with the notation. So this thing here is called the Lorentz factor. And let's just look at what happens to Lorentz factor as we vary this number V here. Of course, if V is 0, then Lorentz factor is going to be 1. Okay, because 1 minus 0, I have a 1 here, square root of 1 is 1. So Lorentz factor being 1 means the time measurement made by both Alice and Bob are the same, right? Whereas if by chance uh, v happens to be something like 0.05 times the speed of light, okay, this column here tells me the ratio of v by c. If v by c happens to be 0.05, Lorentz factor is going to be 1.001. That's a very small difference, all right? And the speed you need to see cause the small difference is 0.05 times the speed of light. Think about that. Speed of light is such a large number, 3 into 10 to the power 8 meters per second. And the difference you see is just a 0.001 difference in the dilated and proper time. So for ordinary speeds of say a car or a bike or something, which is 30, 60, 80 kilometers per second, you have a 30, 60 kilometers per hour here, and you have 3 into 10 to the power 8 meters per second in the denominator. The fraction is going to be so small, you can simply neglect it and say gamma is 1. That's why in everyday life, you don't get to see time dilation. Time dilation is very negligible. To get noticeable time dilations, this is 1.001, 1.02, you have to reach very high speeds that are practically not achievable for all the vehicles and stuff that you use in your everyday life. As you can see, zero point 0.2 times the speed of light or zero point 0.3 times the speed of light, if you travel at that speed, Lorentz factor will be 1.048, 1.091, so on and so forth. And time dilation will be noticeable. For 0.866, the speed of light, Lorentz factor is going to be 2, which means if this was the speed that the rocket that carried Alice was traveling at, if Alice says it took 1 second for light to do the round trip, Bob would say it took 2 seconds instead. If Alice travels at 0.9995 times the speed of light, which is almost the speed of light, then if Alice says it took 1 second for something to happen, Bob will say it took 100 seconds for the same thing to happen. So the closer you go to the speed of light, the more the time dilation. And as you see, the person outside the rocket, like Bob, will always measure a higher number on their clock, whereas the person inside the rocket will measure a smaller number. So moving clocks run slow. Right? Alice's clock is running slow. She's measuring a smaller number. She say just 1 second passed by. Whereas Bob on the outside says 100 seconds passed or 2 seconds passed based on what the velocity was. So moving clocks run slow compared to clocks that are not moving with respect to the system. So moving clocks run slow. And again, motion is relative here. So if you have a clock and there is another clock moving with respect to you, you can always say that that clock is running slower relative to my clock. All right. The time dilation equation has many implications, which we can figure out one by one. One of them I've represented in the form of a cartoon here, which you can read if you want. But we will explore all these implications of time dilation in future videos, which will eventually lead us to a complete study of special theory of relativity. Until then, I want you to look at the time dilation equation and think about it and see if you can uh, draw out any implications out of that to other areas of physics. All right. So until then, keep the fire of science up, and I'll try to reach back to you as soon as possible. All right. See you soon.